In this lesson, we continue our study of digital counters by examining another category, non-binary counters.
In the previous lesson, we emphasized the difference between asynchronous and synchronous counters. Despite certain basic differences, these two types of counters do share one common feature. Both of these counters have the same counting sequence. Whether ripple or synchronous, the counters we studied in Lesson 2 begin at 0 and count up to the largest number in the sequence. In this example, the count goes from 0 to 7 and then back to 0. The mathematical term for this is counting modulo 8. The count begins at 0 and goes up to the modulus -1, 7 in this case. The modulus is the number of states which are available to represent distinct counts. Since one state is used for the count of 0, there are the modulus -1 states remaining to represent other numbers. Therefore, the largest number that can be counted is the modulus -1. With the counters we've studied so far, the modulus has been a power of 2. The reason, of course, is that each flip-flop has 2 states. Adding one more flip-flop to the counter circuit doubles the counting capacity. This is sometimes expressed by saying that these counters have a binary modulus. In this lesson, we are going to study counters that have a non-binary modulus. Our first example will be modulo, or mod 3. The count cycles through the sequence 0, 1, 2, then 0 again. The largest count is 2, which equals the modulus -1. Later, we will examine mod 5, mod 6, mod 7, and mod 9 counters. Remember that each counter resets to 0 each time there is a clock pulse, which is a multiple of the modulus. All of the counters discussed will be built from JK master-slave flip-flops. This is the state table for the JK flip-flop. You should be familiar with it from your study of flip-flops and timing circuits.
Our first example is a mod 3 counter constructed from JK flip-flops. For easy reference, we'll also include the JK state table so that we can easily verify why particular changes of state occur. Underneath the circuit diagram and state table, we'll list the states of the flip-flops. But in this example, we also want to include the flip-flop inputs as well. Tabulating the J and K inputs next to the state will make it easier to see why the circuit behaves as it does. The first step in analyzing a non-binary counter is to examine the circuit and write Boolean expressions for each flip-flop input. These Boolean expressions are called the control equations. The control equations for the flip-flop inputs can be read directly from the circuit diagram. For flip-flop A, the control equations are J sub A equals B bar and K sub A equals 1. For flip-flop B, the control equations are J sub B equals A and K sub B equals 1. Having the control equations at the top of the table will facilitate analyzing the circuit. We can directly determine the flip-flop inputs without constantly having to refer back to the circuit diagram. Initially, let's say that both flip-flops are reset. The next state of the counter is determined by the current values of the flip-flop inputs. Look at the inputs to flip-flop A. J sub A is the complement of B. So at the moment, J sub A equals 1. K sub A is tied to logical 1, so it won't change. At the clock pulse, flip-flop A will toggle into the set state, but what happens to flip-flop B? Well, let's look at B's inputs. J sub B equals A, which is now 0, and K sub B equals 1. So flip-flop B will remain in the 0 state. Therefore, at the first clock pulse, A will toggle to 1, while B remains at 0. To see what the circuit does next, we have to compute the inputs again. The inputs to flip-flop A are both 1. J sub A is the complement of B, which presently equals 1. And K sub A is tied to 1. At the moment, both inputs to B are also 1. K sub B is always 1, and J sub B equals A, which is presently 1. So both flip-flops will toggle after the clock pulse. B sets, while A resets. To determine the next state, we compute the inputs again, following the same procedure. We know that both flip-flops' K inputs are 1, and J sub B is 0 because A is 0. While J sub A is 0 because flip-flop B is set. Therefore, because the K inputs of both flip-flops are 1, both flip-flops pass into the 0 state after the next clock pulse. The counter has reset after the third clock pulse. Thus, the circuit is indeed a modulo 3 counter. It passes through a 3-state cycle, 0, 1, 2, and back to 0.
This circuit employs the natural counting sequence. That is, each state, when interpreted as a binary number, equals the count assigned to it. The 0, state is assigned to the 0 count. The 0, 1 state is assigned to the 1 count. And the 1, 0 state is assigned to the 2 count. The 1, 1 state, which is normally assigned to the count of 3, is not used at all. The reason the 1, 1 state is never used is because the feedback line from B's complemented output resets A whenever B is 1. Due to this feedback line, both A and B can never be set at the same time. This simple Mod 3 counter illustrates two fundamental ideas underlying non-binary counters. First, not all of the possible flip-flop states are used to represent counts. In this example, the B equals 1, A equals 1 state is not used. Second, non-binary counters employ feedback to cycle through the used states without entering an unused state. In this example, the feedback from B's complementary output precludes A and B ever being set at the same time. The counting sequence and the feedback lines are closely related to the design of non-binary counters. In this course, we're not primarily concerned with designing counters. However, it is important to be familiar with some of the design issues. Being acquainted with the basic ideas makes it easier to analyze a particular counter circuit. Here is another Mod 3 counter. We're not going to analyze it in depth here. You'll have the opportunity to do that in the workbook. Instead, we'd like to point out several interesting features of this counter. The first thing to note is that there is more than one way to construct a Mod 3 counter. Also, notice that there are more feedback connections in this counter than in the one we examined a moment ago. Given these differences, do you think that this Mod 3 counter will behave differently than the one studied previously? Indeed it does. This counter does not employ the natural counting sequence, since the 0-0 state is not used. Instead, the counter cycles through the other three possible states. Although it is not immediately obvious, it is the feedback that prevents this counter from entering the 0-0 state. This circuit illustrates that there is no inherent reason why a counter must follow the natural counting sequence. It is often the case that the natural counting sequence is the easiest and simplest to implement. But it is quite possible to have alternative counting sequences. There are usually many ways to design non-binary counters. The alternatives depend on the designer's choice of which counts to assign to which states, and the resulting feedback, which causes the circuit to cycle through the specified sequence of states. Non-binary counters are usually a bit more intricate than binary counters because there will be unused states in a non-binary counter. In contrast, binary counters, like this one, use all possible states to represent numbers. Moreover, binary counters normally employ the natural counting sequence because it results in the simplest circuit. There is no reason to worry about feedback connections because they are not necessary. But with a non-binary counter, some of the states are not used, so the designer has somewhat more choice in deciding which states and what feedback connections to use. Now turn to your workbook and begin with a review of non-binary counters. Continue with the study materials, completing exercises 1 through 5 until directed back to this audiovisual program.
In the remainder of this lesson, we're going to present several different non-binary counters in order to give you an idea of what is possible. We'll focus on modulo 5, modulo 6, modulo 7, and modulo 9. Now let's start with mod 5. This circuit is called a ring counter because of the feedback loops joining the last flip-flop to the first. We could just as easily draw the circuit in a ring to emphasize the point, but this is an awkward representation, so we don't use it often. It does, however, illustrate how the flip-flops are interconnected. The output of each flip-flop goes to its neighbor's J input, while the complemented output goes to the K input. Let's say that initially, all of the flip-flops have been cleared except A, which has been set using the direct set input. This state represents the 0 count. At the first clock pulse, two things will happen. First, flip-flop A will set flip-flop B. This occurs because input J sub B is 1 and K sub B is 0 when the first clock pulse appears. Second, flip-flop A will be reset. Notice that A receives its inputs from the last flip-flop, E, which is presently 0. Because J sub A is 0 and K sub A is 1, flip-flop A resets at the first clock pulse. Meanwhile, the other flip-flops will remain 0. Thus, after the first clock pulse, B is set, but A is now reset. This represents a count of 1. At the second clock pulse, a similar sequence of events occurs. Because flip-flop B is now 1, flip-flop C's inputs are J equals 1, K equals 0. So flip-flop C will set at the next clock pulse. But because flip-flop A is now 0, flip-flop B's inputs are J equals 0, K equals 1. So B now resets, while D, E, and A remain 0. After the second clock pulse, C will set, while B will be clear. The count is now 2. Likewise, after the third clock pulse, D will be set and C reset. After the fourth clock pulse, E will be the only flip-flop which is 1. And after the fifth clock pulse, A will again be set, while all the other flip-flops will be clear. At any given time, only one flip-flop in a ring counter will be in the set state. The flip-flop which is set causes its neighbor to set after the next clock pulse, while it returns to 0. There are only 5 states used in this counter out of 32 possible states. Each of these 5 used states has only one flip-flop set at any given time. All the others are 0. This is hardly the most efficient design. 5 flip-flops are being used to store information that could easily be stored in 3. However, the ring counter does have its advantages. It's an extremely simple circuit with few interconnections and no gates whatsoever. In some situations, the cost of 2 extra flip-flops may be less than the cost of more elaborate interconnections. The ring counter vividly demonstrates the ideas we discussed a moment ago. The design of non-binary counters depends on a choice of which states should represent which counts, as well as the feedback loops which implement the chosen counting sequence. There are other designs for modulo 5 counters. We'll examine one of them later in the workbook.
Right now, though, let's turn our attention to modulo 6 counters. Here's an interesting variant of the ring counter. It's known by several names: switch ring, switch tail, or Johnson counter. The important feature of this counter is the crossover in the feedback lines after flip-flop C. This crossover doubles the modulus of this counter as compared to a ring counter. A ring counter with 3 flip-flops would count mod 3, while a switch ring counter with 3 flip-flops has a modulus of 6. Let's see why. Assume that initially all flip-flops are 0. Neither B nor C will change state, because both of their J inputs are 0, while their K inputs are both 1. However, flip-flop A will change because of the reversal in the feedback from C to A. J sub A is C's complemented output, so J sub A is 1. K sub A is 0 because C is 0. Therefore, at the first clock pulse, flip-flop A will change from 0 to 1. At the second clock pulse, A remains set, and C remains reset. But B changes state. At the second clock pulse, the inputs to B are J equals 1, K equals 0. So B will change into the 1 state. At the third clock pulse, flip-flop C sets as well. Neither A nor B changes. When the fourth clock pulse occurs, however, A resets because of the switch ring connection. At the fifth clock pulse, B resets. And finally, at the sixth clock pulse, C resets. This counter has 6 distinct states. Notice the sequence in which these states are occupied. 3 states represent a progression of 1s, starting at A and moving right 1 flip-flop at a time. Then when all flip-flops are set, the switch tail feedback loops cause A to reset, and a progression of 0s begins, moving 1 flip-flop at a time, just as the progression of 1s did. The counting sequence and feedback loops of the switch ring counter give you an idea of the variety that exists in non-binary counters. The switch ring design can be used to construct a counter of any even-numbered modulus. For example, with 5 flip-flops, a switch ring counter has a modulus of 10. This design can be applied to any modulus which is an even number. The modulus equals twice the number of flip-flops. With a small change in the circuit, the switch ring design can be used for odd-numbered moduluses as well. All that's necessary is to move one of the feedback lines. The operation of this circuit is quite similar to the normal switch ring counter, except that the new feedback connection eliminates the 1, 1, 1 state from the counting sequence. Thus we have a mod 5 counter rather than a mod 6 counter. The switch ring counter, in either of its variants, is a simple and useful design. It has certain drawbacks, but in many applications, it is a very attractive design.
Let's turn now to our next example, Mod 7. Here is the circuit. We won't analyze it step by step here. Rather, we would like to point out several interesting features of this counter. First, this counter is asynchronous. The clock input of flip-flop C is driven by flip-flop B, not the clock. The non-binary counters we previously examined were synchronous, but this is not a requirement. Second, this counter employs gates in the feedback lines. Although this is the first time we've seen gates in this lesson, most non-binary counters are constructed using gates of one type or another in the feedback lines. Look at the counting sequence for a moment. As you can see, this counter follows the natural counting sequence. 0 to 6, and then back to 0. The transition from a count of 6 to a count of 0 is enforced by the 2 NAND gates. This one keeps A in the 0 state when both B and C are 1. While this NAND drives B to 0 if A and C are both set. The feedback loops of this counter force flip-flops A and B back to 0 after a count of 6 is reached. No feedback is required to force C back to 0, since B's output of 1 falling to 0 will cause C to toggle naturally. In the workbook, you'll have the opportunity to analyze this counter and verify that it does function as we've indicated. Right now, just notice its two salient features. This counter is asynchronous, and it employs gates in its feedback lines.
Our final example of non-binary counters will be modulo 9. This mod 9 counter is constructed by cascading two mod 3 counters. You'll notice that the mod 3 counter circuit is one we studied intensively earlier in this lesson. The clock input of the first counter is connected to the signal source, whose pulses are to be counted, while the second counter's clock input comes from the most significant bit of the first counter. This count is read as the combined output of the two counters' individual flip-flops. The LSB is represented by the first flip-flop's first output, while the MSB comes from the second counter's highest order output. Assuming that both counters are initially 0, let's see how the cascade operates. The first counter cycles through its three-state sequence once while the second counter is 0. Once again while the second counter is 1, and once more while the second counter is 2, resulting in 3 times 3, or 9 possible counts. Thus, a mod 9 counter can be constructed by cascading a pair of mod 3 counters. Cascading is a simple and useful way to help build up higher modulus counters from lower modulus counters. For example, a mod 10 counter could be built from a mod 2 and a mod 5 counter. A mod 12 counter could likewise be constructed by cascading a mod 2 and a mod 6 counter. Or mod 12 can be achieved by cascading modulos 4 and 3. Thus, our final example of non-binary counters demonstrates how counters can be cascaded to form larger modulus counters. In the workbook, we'll have more to say concerning this important topic. But now, let's review what we've learned in the second half of this lesson. We studied ring counters and saw an extremely simple but inefficient design that's applicable to any modulus. We examined a variant of the ring counter, the switch ring counter, and saw that it's just as simple but requires only half as many flip-flops as does a ring counter. And we looked at a mod 7 counter, which is asynchronous and which requires gates. And finally, we examined a mod 9 counter, which was constructed by cascading two mod 3 counters.
This concludes the audiovisual presentation for Lesson 3. Now turn to your workbook to the section titled Ring-Type Counters. Continue with the materials and complete exercises 6 through 9. Remember to complete the course evaluation form for this unit when you've finished.